The simplest solution for inrush current limiting problem is by putting a resistor. As we saw in the simulation, putting a resistor will definitely limit the inrush current. So let us put the resistor around this place here. Let us shift it out and then include a resistance like this. So this will be the surge limiting resistance Rs. So how to find the value of Rs? So Rs will be Vi minus Vc. Vc you consider it as 0, worst case condition, and at startup Vi max. So let us say Vi max divided by Rs will be the inrush current limit. So therefore Vi max divided by I in limiting value. So this value can be obtained from, while doing the steady state analysis and steady state design, you would have chosen the diode. From the data sheets of the diode, you will get the non-repetitive peak current rating of the diode, and it should be less than that peak current rating of the diode. Non-repetitive peak current rating. So once you have selected a diode, let us say it has a non-repetitive peak current of, let us say, 50 amps, then you can choose I in limit at around 45 amps or even 50 amps, so that you are within the safe limits during the steady state operation. Now with respect to Vi, what to choose? See, the input voltage is 230 volt RMS, that is the nominal value, but it has a tolerance plus minus 20% in most places. But this plus minus 20% tolerance is a standard number, but it can go to much higher values of degrees of tolerances at different places. So you can accordingly take the tolerance limit according to places. So let us say we have a tolerance limit 230 volts from the nominal. It can go plus or minus. For us, the worst case for this application is plus 20%. So if at the time of switching it was Vi max, which means 230 root 2 plus 20%. So you will see that the range is from 260 volts to 390 volts, corresponding to the plus 20% max. So use this value 390 volts here divided by I in limit, what you want to be the limit, so that you are in the safe region for the diodes. So this is how you have to choose this surge limiting resistor. So if I mark the voltage measurement like this, that is, you are keeping the common probe here and the positive of the probe here, you get VRS because there is a current I in flowing through that, and the I in flows in this fashion as we saw in the simulation, right, in steady state. The job of RS is only during the starting inrush current. After that, it is not needed, but it is there in the circuit. So because of that, you will see that there is a voltage drop which is coming across it due to this nature of current that is flowing through it. So you will have a voltage drop across the resistance in this fashion, having similar wave shape as the current, and that is VRS, which is I in into RS. Now this drop is coming across this, so which means that the voltage across the load V0 will be lesser by that much amount. So therefore you will see that the voltage is lower, the average voltage of the output is lower compared to the one without having put RS. So one of the main advantage of this solution is simplicity. So that is the main pro. Simplicity, you just need one component, nothing more, and it is robust and it will solve your problem and it will make the circuit operable during startup and steady state. However, there are disadvantages. One of the main disadvantages is that it is lossy, because there is going to be a drop, current flowing through it, there will be a loss, and therefore the efficiency of the entire circuit will suffer, will be low. And the second problem is the available voltage at the output is lower, so lower V0, as compared to the case where you don't have RS. So let us look at few other solutions where these disadvantages are removed.